Hello, juniors. Today we're going to start with a new topic, which is still part of functions, but it's a new type of function that we're going to be studying, which is known as the reciprocal or rational function. Okay, so up to now we have seen the initial concepts of a function. We've seen domain, range of a function. We've seen asymptotes. We've seen composite functions, inverse functions. We've seen transformation of functions. And then we have studied two particular types of functions, which were linear functions and quadratic functions. So now we're going to start with a third type of function, which is the reciprocal or rational function. So the objectives for today's class: first of all, identify reciprocal functions. Then find the reciprocal function in the form 1 over x, its graph and self-inverse nature. Then determine vertical and horizontal asymptotes. And finally, identify a rational function and its graph. Okay, so to begin with, we're going to start by defining what a reciprocal function is about. And it says, the reciprocal function has this form: f of x equals k over x. So k is any number. It is a constant. It could be 1, 2, negative 4, whatever. And x is the variable, right? So the graph of a reciprocal function all have similar shapes. And just to give you an idea, this is the general shape of a reciprocal function, right? This part over here and this part over here are, and these are also known as hyperbola, okay? So this is the shape of a rational function, okay? So then it says, we're gonna do this short investigation together. It says, graph of reciprocal functions. Use your GDC to draw all the graphs in this investigation. So we're going to be drawing this function, this function, this function to begin with. And we're going to analyze what is the effect of changing the value of the numerator. You see how this is 1, 2, 3. Okay, so let me go to Desmos. Here I already made the graph, but I'm going to erase it just a second. So here you see this is the red function, which is 1 over x, okay? So you see that this is a rational function. You see that we have one hyperbola on the first quadrant and the second hyperbola in the third quadrant. Then if I draw the second, you see that the shape is exactly the same, but it is kind of less steep, right? But the general shape, and you see that the asymptotes are also the same. If you remember, the asymptotes of a function are lines that the function never reaches. And in this case, both the lines x equals 0, the vertical line x equals 0, and the horizontal line y equals 0 are both asymptotes of these functions. Finally, if I draw 3 over x, the third one, you see that it's the same thing and it has the same general shape, but it's a little bit less steeper than the first function. Okay, so if we go back, what is the effect of changing the value of the numerator? Basically, what we're doing is we're stretching the function, right? But we're not changing its position or the asymptotes or nothing like that. We're just stretching the function. Now, for part 2, it says, draw the graph f of x equals negative 1 over x, negative 2 over x, and negative 3 over x. So same thing as before, but now we're adding a negative value in front. What do you think should happen when I add a negative value in front? So let's see. Let me erase this 2 for now, and I'm gonna write the equation negative 1 over x, negative 1 over x, then negative 2 over x, and negative 3 over x. You see what's happening here? Let me erase the first one, this one. You see that we obtained the same functions, but now we're in the opposite quadrants. Before, let me erase this 2 for a second. Before we were in the first and third quadrant, right? And by adding a negative sign in front of the function, we are reflecting the original function to reflecting on the y-axis, right? So we are, y or x-axis, actually both are correct, Okay, so we're now working with the other two quadrants, second quadrant and fourth quadrant. Okay, so that's what occurs when we add a negative sign in front. And you see that if we change the numerator, 1, 2, 3, the only thing we're changing is the stretch, just like as the previous exercise. Okay, so what effect of changing this? What is the effect of changing the side of the numerator? We're having a reflection on the y or x-axis too. Both, in this case, both things are the same, right? If we reflect it on the x-axis, we're gonna get the same functions or the same graph. Okay, then part 3, it says copy and complete the following table for f of x equals 4 over x. In order to save some time, I already plugged in the values, but basically what you need to do here in order to find these values that I wrote here is replace the values of x to find the value of y, right? For example, for 0.25, we're going to do 4 divided by 0.25, and that gives you 16, okay? And then you do the same for the rest of the values to find all of this. And this is the table for this particular function, a reciprocal function for 4 over x. So let's discuss these questions. B, what do you notice about the values of x and f of x in the table? What do you notice here? As you see that the values of x are increasing, right? And as I increase the value of x, what happens to the values of y? They are decreasing, right? So that's what you should notice, right? Let me write this here. They are, x and y are inversely proportional. We call that in math. Inversely proportional. That means that as x increases, y decreases. Okay? Then it says C, draw the graph for the function. If I draw this graph here, let me erase all of this. I'm going to put the function 4 over x, 4 divided by x. This is how the graph looks like, right? So basically it has the same shape as the ones we were drawing before. So I already took this graph here. It's this one. I only took the first quadrant for the investigation. So we already drew the graph. You can try doing this in your calculators. And then it says D, draw the line y equals x on the same graph. Remember, the line y equals x is a 45-degree line, right? So if we draw this using blue, maybe, this line over here would be the line y equals x. And y was, or when did we use this line? This line was used in order to find the inverse of a function. Remember, we said that the inverse of a function is a reflection of the function into this line, y equals x. Like this line acts like a mirror in this case, if we want to find the inverse. Okay, so we already did part D. Then part E says reflect f of x in the line y equals x. So basically what we're asked to do is to find the inverse of this function. Pay attention, because this is something interesting. If I identify the important points of this graph, for example, I'm going to plot all of these points. 0.25, 0.25 and 16. Well, I cannot put that. 0.4 and 10. 0.4 and 10 would be this point over here. So I'm going to write 0.4, comma 10. Another point is 8 and 0.5. That's, sorry, 0.5 and 8. That's right here. So 0.5 and 8. Then if 1 and 4 is also another point. 1 and 4, that's here. 1 comma 4. And then I'm gonna 2 and 2, that's another point, but I'm not gonna put put all of the points because we're going to waste too much time. So I'm going to put this one, which is 4, 1. Then we have 8 and 0, 5. That's here. 8, 0.5. And one more, maybe this one, 10 and 0.4. 10, no, I'm going to do the other one, 16 and 0.25. This one over here. 16, 0.25. Now, pay attention. If we want to find the inverse, remember the process is that we need to flip the points, right? So we're going to write, instead of this, we're going to write 10, 0.4. Then this one would be 8, 0.5. This one would be 4, 1. Then this one would be 1, 4. 1, 4. Then this would be 0, 5, 8. And finally 0.25, 16. So if I plot these green points here, pay attention to what will happen. For example, 10 and 0.4. 10 and 0.4 is right here. This point over here. Then 8 and 0.5. 8 and 0.5 is exactly this point over here. Then 4 and 1. 4 and 1 is exactly this point over here. There. Then we have 1 and 4. 1 and 4 is exactly this point over here. Then 0.5 and 8. 0.5 and 8 is exactly this point over here. And finally, 0, 25 and 16 is exactly, well, I cannot draw that point because it's out of my reach. But if you noticed, I'm basically plotting the same points. So if I graph the inverse function, I will be having exactly the same function as the original one. Okay, something like that. So that's an interesting property of reciprocal functions. So what do you notice for part F? We notice that the same curve is drawn, right? The same curve is drawn. So for part G, it says, what does this tell you about the inverse function? It tells us that it is the same function, basically. It is the same function. And this property is called the self-inverse nature. Self-inverse nature. We're going to see this with an example later on. But this is the self-inverse nature. It means that the inverse of this function, it's the same function, okay? That's what self-inverse nature is about. And that was one of the objectives for today's class. This one, it's graph and self-inverse nature. Okay, so let's move on to discuss the properties of reciprocal functions. It says, if a curve gets continually closer to a straight line but never meets it, the straight line is called an asymptote. So here we have the definition of asymptote, which is something that you already know. Okay, then it says, y equals b is an asymptote to the function y equals f of x. It's just explaining this graph over here. As x approaches or tends to infinity, the function approaches or tends to b, but it never actually touches b, okay? It infinitely approaches that value, but it never reaches it, okay? So the symbol and this arrow means approaches or tends to. Then it says, the graph of any reciprocal function of the form y equals k over x has a vertical asymptote at x equals 0. If you see this graph, for example, the one I did at the beginning, x equals 0 is this vertical line over here. And a horizontal asymptote, y equals 0. Horizontal asymptote, y equals 0 is basically the x-axis, right? So a reciprocal function will always have two asymptotes, a vertical asymptote and a horizontal asymptote. The position of each asymptote will depend on the function, but the original or the parent function of a reciprocal function which has this form will always have vertical asymptote x equals 0 and horizontal asymptote y equals 0. Okay, then it says the horizontal line y equals b is a horizontal asymptote of the graph y equals f of x. Okay, we already know that. Then it says the graph of a reciprocal function is called a hyperbola. Okay, so as we call the quadratic function, we call it a parabola. Now for the reciprocal function, we're calling it a hyperbola. Okay, and it's basically this and this. So properties. The x-axis is the horizontal asymptote, as you can see here. Then the y-axis is the vertical asymptote, as you can see here. Both domain and range are all real numbers except 0, right? You see that for the domain, remember the domain are x values. This function can take all of the values of x except x equals 0 because there is a vertical asymptote for that value, right? The function never reaches 0. And the same thing occurs with the range. Range are the y values of the function. You see that this function comes from infinity and it goes down to infinity, but there's one value here, which is y equals 0, that the function does not take because there is an asymptote there, a horizontal asymptote. So the range is all real numbers except y equals 0. Okay? So domain x different from 0, y is and range is y different from 0. That is the domain and range of a reciprocal function always, whenever it does not have any type of transformation, okay, or translation actually. Then it says both the domain, okay, I already read that. Then it says the two separate parts of the graph are reflections of each other in y equals negative x. Y equals negative x is this line over here. So you see that is like a mirror which reflects this function into this function. Okay, then it says y equals negative x and y equals x are lines of symmetry for this function. So this is a line of symmetry and this line over here is also a line of symmetry. That's what it's telling. Okay, so I hope you understand these properties for the reciprocal function, also known as hyperbola. Then we have limits and asymptotes. What is a limit? This is a concept that we're going to be studying further when we study calculus, which is a topic for the senior year. But I'm going to introduce this concept just for you to have an idea of what this is about. So a limit is the value y which a function f of x is tending towards or approaching towards, but does not reach as x tends or approaches a certain value. Okay, so that's the concept of a limit. It is very related to the concept of asymptote. Okay, so it says the first limit of the function f of x equals 1 over x, this is a reciprocal function, is limit of the function when x approaches positive or negative infinity, and this is 0. Basically what this is saying is, if you look at this graph, if we keep on increasing the value of x until positive infinity, this function will reach a value which is very close to 0, right? Because it will keep on approaching the asymptote, which is 0. Okay? And if we do the same for the other side, if we keep on increasing the values of x until negative infinity, the function keeps on approaching the horizontal asymptote, which is y equals 0, right? So in the limit, when the value of x is a very big number, that is infinity, then the value of the function would be 0, okay? That's how you interpret limits in this case. Okay, then it says, this means that as x tends towards either positive or negative infinity, f of x tends towards 0, which is what I just showed you. The second limit of the function, f of x equals 1 over x, are this. Limit of f of x when x approaches 0 from the right, that is what the plus means, is infinity. And the limit when the function approaches 0, when x approaches 0 from the left, that's what the negative sign implies, is negative infinity. What does that mean? Just take a look at this. If I'm approaching from the right, that means I'm looking at the function from right to left. You see that this function, when we are coming from this side, is increasing towards positive infinity, right? So when we approach from the right, which is this first case, it says that the value of the limit is infinity because the function just goes to positive infinity. But if I'm approaching, let me change this. If I'm approaching from the left, that's from left to right, you see that this function is going down towards negative infinity, okay? So that means that what we have here, if I'm approaching from the left, that's why we have the negative sign, the function tends to negative infinity. That's how you read this. So it says, this means that as x tends towards 0 from the positive side, f of x tends towards infinity. And as x tends towards 0 from the negative side, f of x tends towards negative infinity. Note, we say tends towards as it never actually reaches this value. So that's the concept of limits, okay? Then we have this. It says, when sketching the graph y equals f of x, we represent the limit f of x when x approaches either positive or negative infinity equals 0 by drawing a dashed horizontal line called an asymptote along y equals 0. This indicates that f of x tends towards but never reaches 0 and x gets very, very large. We also represent the limits f of x when x approaches 0 from the right equals infinity, and the limit of the function when x approaches 0 from the left equals negative infinity by drawing a vertical asymptote along the line x equals 0. This indicates that f of x tends towards but never reaches infinity as x gets close to 0. Basically, what this is telling us is that whenever we graph a reciprocal function, we always need to keep in mind that this the horizontal asymptote is y equals 0 and that the vertical asymptote is x equals 0, okay? That's basically what all of this text is saying. Here's some curious fact. It says the word asymptote is derived from the Greek asymptotos, which means not falling together. They never reach or they never touch each other. Okay, some applications, some real-life applications of reciprocal functions. We can find this, for example, in supply versus demand curves. Maybe you have seen this already in business, but you'll see that the curves look something like this, right? Which is the first piece of the hyperbola, like you see here. Then we have length of guitar string versus frequency of vibration. The shorter the length of the guitar string, the higher the frequency of vibrations. So they are inversely proportional, which is a property that we saw in the beginning, in the first investigation we did. Then designing water slides for aquaparks. The water slides tend to be like this, very steep at the beginning, and then at the end, when they reach the pool, let's say the pool is here, it gets horizontal, right? So this has the shape of a parabola as well. Then designing skate ramps, same concept. The skate ramps are like this, or well, that's very something like this, right? Maybe we can build the structure here. And here comes the guy with the skate. Something like this. This is very imprecise, but you get the idea, right? The shape of the skate ramp is a reciprocal function. Then crowdfunding calculations. That's basically whenever you want to calculate how much you need to pay. Let's say you're all buying I don't know, a gift for one of your classmates, and the gift costs 100,000 guaraníes, for example. So if you want to calculate how much each of you need to contribute for the gift, you calculate it this way. Let's say contribution equals 100,000 guaraníes divided by the amount of people that want to contribute for the gift, okay? So the greater the number of people that want to contribute, the less that each one will have to pay, right? And if this number is small, then each of the students will have to pay more, right? So this inverse proportion between the variables is what reciprocal functions is about, okay? And that's crowdfunding calculations, basically. Okay. Moving on with this, I told you that we were going to see the self-inverse function property with an example. So the question is, what is the inverse function of a reciprocal function? So let's say that the reciprocal function is f of x equals 1 over x, okay? This is an example of a reciprocal function. So we want to find the inverse of this function. So let's follow the process that we already learned in the previous chapter. Actually, the first one we covered in the year. If we want to calculate the inverse, the first thing we need to do is write this as y equals 1 over x, right? Then the second step is to switch y with x with y. So this would be x equals 1 over y. And then we need to solve for y, that is, leave the y alone, right? So I can take this y up here and take this x down here in order to leave the y alone. And we will have that y equals 1 over x. So the inverse function would be f minus 1 of x, the inverse function, equals 1 over x. But the original function was 1 over x, right? So we see that the inverse function ends up being exactly the same as the original function. And that is the self-inverse function. It's that the function and its inverse are the same, right? So we saw algebraically how that occurs, and we've also seen graphically through this example how that occurs, right? So that's the self-inverse property, which occurs for reciprocal functions. Okay, so to finish this class, we're going to do this short example to finish grounding the idea of what reciprocal function is about. So it says, for each function, write down the equations of the vertical and horizontal asymptotes, sketch the graph, and state the domain in range. We're going to do this without the help of a calculator. So part A. The function is y equals 9 over x. You should already know by now that this is the equation of a reciprocal function, right? So if we make a quick sketch of this, you see that there are no vertical nor horizontal translations, right? So this graph should look just like as a normal reciprocal function. That is, here in the first quadrant, the first piece of the hyperbola, like this maybe, and the second part of the hyperbola like this, okay, in the third quadrant. So this is a sketch of the graph. Then what will be the vertical and horizontal asymptotes? The vertical and horizontal asymptotes are, vertical asymptote is x equals 0, and horizontal asymptote is y equals 0, right? So okay, actually that was part B, so I'm gonna take this down a little bit. Do you remember how to determine the horizontal asymptote, or sorry, the vertical asymptote mathematically? Remember the rule, it was set the denominator to 0, right? And in this case, the denominator is directly x. So x equals 0 is the vertical asymptote, right? That's another way of determining the vertical asymptote. So for the first part, we're going to say that the vertical asymptote in this case is x equals 0, and that the horizontal asymptote in this case is y equals 0. Okay, so then we have the graph, the sketch of the graph, and finally we're asked to write the domain and range. Since we have these two vertical asymptotes, the domain and range, or the domain would directly be all real numbers except this value, and the range would be all real numbers except this value. Okay, so basically domain x different from 0, and the range y different from 0. Okay, so that's it for the first exercise. Now for part B, I'm going to do that here. You see that we have exactly the same function, but now we have a +2 over here. If you remember from function transformations, you should remember that this +2 is causing a vertical translation 2 units up. So that basically means that all of this function would have exactly the same shape, but it will be displaced 2 units up, right? So if I do a sketch of this, let me copy this for a second. Basically, what we're going to be saying is that since all of this is shifted 2 units up, that means that my horizontal asymptote will not be y equals 0 anymore. It will be y equals 2 because it is shifted 2 units up, right? So if I put here, for example, this is a sketch, so I can assume it is there. I could say that this line corresponds to y equals 2, right? I'm going to say this is a 2 over here. So the graph would look exactly the same, but it would be now displaced 2 units up. So my hyperbola would be here and here. Wait. Here, okay? It has shifted 2 units upward. So the vertical and horizontal asymptotes would be, in this case, the vertical asymptote is still the same. It's x equals 0. But the horizontal asymptote is now y equals 2 because of the vertical translation. Let me write that here to remember. This is a vertical shift. Like that. This is a vertical shift 2 units up. Okay, so that's why the horizontal asymptote moves 2 units up. And finally, the domain and range follows the same rule as the previous exercise. We just look at the values of the asymptotes and we say x should be different from 0 and the range is y different from 2, okay, because the horizontal asymptote is y equals 2. And that's it. That's it for this class. I hope this was clear enough. This is reciprocal functions. As always, if you have any doubts, please let me know. And that's it. See you, juniors.